Hey guys, I want to show you how to rationalize denominators real quick. A lot of people are comfortable with this with square roots, but it gets a little bit more difficult with cube roots. So I kind of want to spend some time on both and just explain a little bit of what's going on. Alright, so the idea is that we want to rationalize denominators if we ever have a radical in the denominator. Like if I have, just say 1 over the square root of 3, I want to rationalize that. The point is that the square root of 3, that's a decimal that goes on forever. If I pull up the calculator and I take the square root of 3, it's an irrational number. This calculator approximates it pretty well, like a lot of decimal places, but still it goes on forever, so there's a lot that's not here. And remember that when you're dividing decimals, if I had 732, continuing on forever, and I wanted to divide that into 1, you can't really divide by decimals, so you got to move the decimal over as many times as you need to get rid of it. But in this case, the decimal goes on forever, so there's no way to move it an infinite number of times. You can't actually do the division with a decimal, with an irrational number. So the idea is that we got to get the radical out of the denominator. And so for square roots, a lot of times what people think that you do is you just multiply by the square root, the same square root. Like for example, people say, well, you can multiply the top and bottom by the square root of 3. This is an expression, so whatever I do to the bottom, I have to do to the top. But then that gives me the square root of 3 over the square root of 9, which is just the square root of 3 over 3. Now there's no more radical on bottom. These two are the same. 1 over square root 3 is the same as the square root of 3 divided by 3. The difference is now that I can actually approximate it, I could put the 1.732 whatever on the inside and just divide by 3, no problem. 3 goes into 1 0 times, 3 goes into 17 5 times, and continue on as many times as I want to approximate what this actually is. So there's no way to divide by a decimal that goes on forever, but now I can divide into a decimal. That's no problem. But I kind of want to change that thinking because the truth is that there's a little bit of a shortcut or a little bit of a better way to rationalize. What I mean is, if I make a new page real quick, say I wanted to rationalize 3 over the square root of 8. Then you could multiply top and bottom by the square root of 8 over the square root of 8. That's what I'm saying a lot of people think to do. The square root of 8 times the square root of 8 is going to be the square root of 64, but I already know the square root of 64 is actually just 8 without the radical, right? So it would have been the square root of 64, but that's really just 8, so there's no real reason to write it. When you multiply the square root of 8 times the square root of 8, you just get 8. Actually, that's true for any square root, so you can just take that shortcut every time. The problem here is that now I still have to simplify the square root of 8. The square root of 8, remember, is 4 times 2. So I can separate it to be the square root of 4 over the square root of 2. But then the square root of 4 is just 2. This 2 stays inside the radical. And then all over 8. So that really I have 6 root 2 all over 8. Well, now that I've simplified the radical, I have a fraction that I could reduce. So I got to divide top and bottom by by 2, so that I get 3 square root of 2 over 4. 6 over 8 reduces to 3 over 4, and finally I'm done. That's kind of a long, tedious process, and the truth is it doesn't have to be. So if I start with the problem over again, 3 over the square root of 8, rather than just always multiplying by the square root that's down here, it's better to ask yourself, what's the smallest possible square root that I can multiply by to make the inside a perfect square? Like 8 goes into what perfect square? Well, I know 16 is a perfect square. If you have your list of squares, that would help. 8 goes into 16, so if I multiply just by the square root of 2 on top and bottom, then I'm really done in one step, because the 3 square root of 2 on top over 8 times 2 gives me 16, and when I take its square root, I get 4, right? It's really the square root of 16, but I can just take that square root and get 4. So I'm done in one step. Look at how much space I save, how much work I save. So the idea is that really you want to multiply by the smallest number that you can to make a perfect square. Now it's not always possible. Like if I have, say, the square root of 7 over the square root of 10, 10 doesn't go into any other perfect squares except 100. So if I multiply by another square root of 10, I get the square root of 70 over the square root of 100, which is just 10. Of course, I should try to reduce the square root of 70, but it doesn't reduce. So in this case, that's the best I could do. But what I'm saying is, if I had, say, the square root of 3 over the square root of 20, it doesn't seem like a good idea to multiply by the square root of 20 anymore. Why? Because if I just look at my list of squares, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, I get 1, 4, 9, 16, 25, let me just keep going, 36, 49. So far 20 is not going into any of these. 64, 81, but 20 does go into 100. So I don't need to multiply by the square root of 20. In fact, if I just multiply by 5 on bottom, I'll get the square root of 100, which is just 10. I've been skipping that step. There's no reason to really write this. You can take that square root in your head. So 20 times 5 gives you 100. We did that on purpose, so we know its square root should have been 10. But whatever I do to the bottom, I have to do to the top. I multiply 3 times 5, I get the square root of 15, and that doesn't reduce, so I just leave it as the square root of 15 over 10. Here's another way to think about it, though, and here's an easier way to actually see it. So I like that way of thinking. It's very helpful, but if I go back to the square root of 3 over the square root of 20, I can see that 20, if I break it all the way down using a factor tree, is 2 times 10, which is 5 times 2. So there's 2 2's and a 5 on the inside. I know that 2 times 2 gives me 4. I can take its square root. But if I had an extra 5 in the square root, then I would have a pair of 5's to come out also. So I can ask myself, what's missing? Remember, for a square root, I need pairs of 2 in order for 1 to come out. If I have a pair of 2 2's, a 2 already comes out and leaves me with the square root of 5. But now one more square root of 5 is going to make the 5 come out to give me 2 times 5. So the logic is break 20 all the way down, see what's missing. You have a 2, and a 5. So one more 5 will actually get rid of the radical. That becomes the square root of 15. A 2 and a 5 come out. 2 times 5 gives me 10. Let me see. Let me pull up another one from Math Excel maybe. This one is the square root of 5x over 28, all inside one radical. So the idea is that it's not rationalized because this is really the square root of 5x over the square root of 28. But if you break 28 down, you know that 28 is 14 times 2, which is 2 times 7. So you have a 2, a 2, and a 7. The question is, what else do I need in order to cancel out the radical completely? 2 2's are already going to bring a 2 out of the radical, right? 2 times 2 gives me 4. When I take its square root, it just comes out as a 2. But if I multiply by one more square root of 7, now I have the square root of 7 times the square root of 7, which just gives me one more 7, again, outside of the radical. So the truth is, if I just multiply by the square root of 7 over the square root of 7, I get the square root of 35x over, I could multiply 7 times 28. 7 times 28 is 196. But then the square root of 196 is just 14. The truth is, I already knew the answer was going to be 14 because I pulled out a 2 and I pulled out a 7, and 2 times 7 gives me 14 down here anyway. So then my answer is just 35, square root of 35x all over 14. Let me show you one more just like that. If I had the square root of 7x over 50, That's the square root of 7x over the square root of 50. But 50 breaks down to be 5 times 10, and that's 5 times 2. So inside of the square root, I already have 2 5s, but I need one more 2 in order to get rid of the radical completely. These 2 5s bring a 5 to the outside. If I were to multiply by a square root of 2, then a 2 would come out as well. So multiplying top and bottom by the square root of 2, I get the square root of 14x over the square root of 100, which is just 5 times 2, which is 10. And so a lot of people say, well, wait a second, couldn't I just simplify the radical first and then try to rationalize it using that same logic? And you could. That's a good actual observation for square roots. The problem is it doesn't necessarily work for cube roots. So what's the problem with cube roots? The problem is that if I had 6 over the cube root of 2, it's not good enough anymore to just multiply the top and bottom by the cube root of 2. Because look at what happens. I end up with 6 cube root of 2 over the cube root of 4. And then I would say, well, what's the cube root of 4? You might be thinking that it's 2, but that's the square root of 4. There is no cube root of 4. If you look at your list of cubes, 4 is not on there. You can't take the cube root of 4. So the truth is, you got to do that same sort of thing. You got to say, okay, well, what should I multiply if I have my list of cubes? I have, If I have 1 cubed, that gives me 1. 2 cubed gives me 8. 2 could go into 8. So if I had If I had 6 over the cube root of 2, I shouldn't multiply top and bottom by cube root of 4, but by the cube root of 2, I should multiply by the cube root of 4. Because now I get 6 cube root of 4 over the cube root of 8. And at least then I know what the cube root of 8 is. It's 6 cube root 4 all over 2. So the point is, just like I said before, you want to ask yourself what's the smallest perfect cube that 2 goes into. So then you can say, well, 2 goes into 8. I just have to multiply by a 4 to make it an 8. That gives me 3 cube root 4 after I'm done simplifying. In truth, you might have something that has a little bit more factors. Like maybe I give you, say, the cube root of, well, let me just do 3 over the cube root of 20. Like I was saying before, you can break 20 down. We already did it. It's 2 times 2 times 5, right? It's 4 times 5, which breaks down to 2 times 2 times 5. The difference with cube roots versus square roots is that you need triples in order to bring 1 out. Meaning if I multiplied by the cube root of 2 only, a 2 times a 2 times a 2 gives me an 8, and the cube root of 8 is 2. But then that leaves me with a 5 on the inside. So not only do I want to multiply by a cube root of 2, but I also want to multiply by 2 more 5s, 1 5 and 2 5s, so that I can pull out a 2 and a 5, right? 5 times 5 times 5 gives me 125, and its cube root is 5. So the truth is that if you can factor this all the way down, then you can just ask yourself again, like we were saying with square roots, what's missing? I already have 2 2's. I'm dealing with a cube root, so I need triples in order to bring 1 out. That means that if I give it an extra 2 and 2 more 5s, then on bottom I'll get 2 times 5, which is 10. By the same logic that I just said. But whatever I do to the bottom, I have to do to the top. 2 times 5 is really a 50. So that I'm left with the cube root of 50 over 10. 3 cube root of 50 over 10. So a lot of people get weirded out by that. If you want to, you could just multiply top and bottom by 2 times 5 times 5, and then say, well, 2 times 5 times 5 is 50. And then on bottom, 50 times 20 gives me 1,000. Its cube root is 10. Of course, you should reduce if possible. The radical doesn't simplify, so I'm done there. Let me do it all together again. Say I had say I had 5 over the cube root of 16. 16 is not a perfect cube. 16 breaks down to be 4 times 4, which is then 2 times 2 and 2 times 2, so that I have the cube root of 2 times 2 times 2 times 2 4 times. These 3 could already come out of the radical. Let me be a little bit more careful when I underline that. These 3 can already come out, but this 2 doesn't have anybody to come out of the cube root with, right? So this is already a single 2, but then I need to give this 2 friends to come out of the cube root with. So I multiply by 2 more 2's on top and bottom so that an extra 2 comes out. These 3 2's inside of a cube root bring out a single 2 on the outside. So the truth is, I'm multiplying by 2 extra 2's, the cube root of 2 extra 2's on top and on bottom. So that I'm left with 5 cube root of 4 on top. You could do 2 times 2, which is 4, times 16, which is 64, and then try to take the cube root of 64. But what I'm telling you is you already knew that a single 2 was going to come out and another 2 was going to come out, so that you get a 4 here. Otherwise, you got to rewrite it as the cube root of 64 first, and then ask yourself what's the cube root of 64? It's just 4. Either way is fine. And so this logic works great for actually any radical. Like if I gave you, say, instead the fourth root of 81 over 125. Well, then I could rewrite this as the fourth root of 81 over the fourth root of 125. 81 is a fourth power. 81 is 3 to the fourth power. So if you have your list of fourths, if you write out a list of fourths, you'll see it's 3. But 125, that is not a fourth power. It's a cube. It's 5 times 25, which is 5 times 5. So the fourth root of 125 is really just 5 times 5 times 5. For fourth roots, I need groups of 4 in order to bring a 5 out, meaning that I have to still multiply by 1 more 5. If I multiply by 1 more 5, then now that I have a group of 4 inside of a fourth root, a single 5 comes out. If you multiply by a single 5 here, multiply top and bottom by the fourth root of 5, you get 3 fourth root of 5 all over 625 inside of the fourth root. But there's no real reason to write that because you already know that you've put together 4 5s, so a single 5 is going to come out. You could always ask yourself, what's the fourth root of 625? But that is just 5. That's the furthest you could go. Okay, so I want you to go back and try a few of these. I put probably 4 problems on the pre-problem of the day. Some are square roots, some are cube roots, there's one fourth root problem. But I really want you to try to perfect this logic here. That way, if you have problems with it, you can ask the questions in class. It's a weird topic to start until you understand it, and then it's not. So the benefit of watching the video beforehand is that now I can know whatever's confusing me going into the class. All right, so try them out. Let me know what you think.